Hello Cave Dwellers, we're in the cave today for a two-part lecture by Professor Steve Furber. If you've not heard of him before, you're in for a real treat. His career touches 5 decades, inspiring the first generation of home computer users in the UK, creating the ARM CPU and designing a replica of the human brain will all feature today. These talks and indeed our museum is made possible thanks to the support of you the viewer, our wonderful patrons and our sponsor PCBWay.com. It doesn't feel right making a comedy sponsor slot in such prestigious company today, so we thank PCBWay for their support and recommend you check them out for their PCB design and manufacturing services, 3D printing, injection molding and CNCing. And of course check out their shared projects where you'll find accessories for computers, including those created by Professor Furber. Visit PCBWay.com. And now for part 1 of this wonderful lecture.
Well, thank you very much for that introduction. I'm now Professor Emeritus at the University of Manchester. Basically, the emeritus thing means that the university has stopped paying me because I've retired, but they haven't completely disowned me. So, what am I actually going to talk about? Here's the outline of my talk, beginning from little acorns, and that's the history stuff, probably the stuff you're most interested in. I'm going to talk a little bit about the research I led at Manchester over the last 25 years under the title Building Brains. And it's not unrelated, it builds on the history. I'm going to finish by giving you a very quick overview from the perspective of the ARM of what 40 years of Moore's Law means. Okay, has everybody heard of Moore's Law? Most of you are nodding, we'll get to it anyway. And then draw a conclusion. And my guidelines are to talk for a sort of hour and a half. So if that's too long for anybody, you're welcome to come and go as you see fit. So starting with little acorns. Now, again, often I ask questions about this, but since the answers to those questions are written on notes around the museum, this might not work very well here. Has everybody seen one of these before? So you know what it is. There's one over there, I think, isn't there? It's the Science of Cambridge MK14. And one of the first things I did when I got involved in the embryonic acorn was I debugged an MK14 prototype. Somehow they'd managed to take the National Semiconductor Development Kit ROM and copy it into 2 PROMs and get some bits wrong. Now, I don't know how you do that, but anyway, I had to work out what was going on there. And then we got involved in building fruit machine controllers for a company in South Wales called ACE. And I think this middle picture is the back of the fruit machine and the right-hand picture is the front. And in this computer, we used 2 National Semiconductor SCMP processors, one of which was effectively timing the wheels, and the other one of which I think was doing some higher level control, handling the money or something. This was just when people who built fruit machines were beginning to want to move from fully electromechanical control to microprocessor control, so that they had better management of the odds, i.e. the machine would pay out less. And this was early work from CPU. But then, I guess you know that the company started as Cambridge Processor Unit Limited. I was not working for them at this time. I was kind of moonlighting. I was employed as a research student and then research fellow in the university at Cambridge. But I got interested in amateur computing, and so sort of did little bits of things with the embryonic acorn, which started off with this, I think Sophie Wilson describes this as an Austrian's idea of a joke, a company called Cambridge Processor Unit, or CPU Limited. Now, shortly after that, Sophie looked at the MK14 and made her usual comment, which was sort of, I can do better than that. And Sophie went away, I think over the Easter vacation, and came back with a design for a similar unit based around the 6502, which she much preferred to the SCMP, and that became the Acorn System 1. It's based on similar principles, so it has a hexadecimal keypad, a 7-segment display which can be coerced into displaying hexadecimal digits with appropriate driving software, and then the baseboard which has the processor and memory and other stuff on it. And this System 1 was built on a PCB which was Eurocard format, so it's the standard size of circuit board, so that you could then plug it into a rack. The connectors down this side would form a backplane that you could then use to plug in multiple boards. And I think we'll get to that a little bit. But before we move on from the System 1, let's see how this goes down. How many people recognise that? Yes, what was it?
Blake 7.
Yes, Blake 7. Who remembers Blake 7? This really is one way of detecting the age of the audience. Blake 7 was, I think it was a BBC series, set aboard a 22nd century cargo transporting spaceship. And at the centre of the control of this spaceship was this computer system, which you can see in the middle is an Acorn System 1, if you look closely. Now, around this time, you may remember, if you're old enough, that Clive Sinclair was claiming you could run a nuclear power station with a ZX80, which was, of course, a completely unsupported claim. But anyway, our counterclaim was you could run a 22nd century cargo spaceship with an Acorn System 1, which was clearly more challenging. So those Eurocards got plugged into racks and used to produce quite professional control systems. And Acorn was selling these in modest numbers. So this has got a CPU card, presumably behind one of these blank front panels. It's got a couple of floppy disk drives, 5.5 were they? 5.25? 5.25. Yeah, my PhD thesis is written on an 8-inch floppy disk. Not many people have come across an 8-inch floppy disk. And I hate to think what I'd have to do to recover the data from it now. You can see things on the front, that's obviously a prom blower of some sort. I'm not quite sure I know what the other bits are. There's a power switch over there. I can give you that one. So you could build a fairly flexible set of modules, and Acorn sold these in modest numbers for industrial control. But if you had a full double rack like this, you were probably talking about £2,000 or something to buy the machine. And Chris Curry, whose name most of you will be familiar with, came out of the Sinclair line, and he was very keen to produce computers that could be sold to consumers. He was always a bit competitive with his former boss. And so Acorn developed this machine. There's one here, yes. So you have got an Atom. This was developed by Chris and mainly by Nick Toop. And Chris and Nick disappeared for a month or two to go and develop the Atom. And it was quite successful. Acorn sold about 12,000 of these. It was initially sold in kit form, which was quite exciting. I think the most memorable one that came back, not working, of course, quite a lot were returned not working because their purchasers had failed to get them to work. But the one notable one came back with an explanatory note that Although the instructions said to solder the chips in, this person knew that chips were sensitive to heat. So they'd been more careful with them and glued them in. And it still didn't work. If you're familiar with the insides of the Atom, it had some quite exciting features. For example, the keyboard is sort of on the top or the back of the PCB, and all the chips are on the other side. So if they're in sockets and you bang the keyboard enthusiastically, eventually the chips drop out. And it used a 7805 linear regulator to generate the 5 volts on the circuit board. And particularly if you added a few things on the inside, such as an Econet network adapter, the 7805 would get sufficiently hot that it would melt the solder and drop out of the board, which wasn't very good. What we said then was, okay, the computer stopped working, but at least you've now got a sound generator if you shake it. So the Atom really established Acorn in the personal computer market, and the name became known among many others. It's hard to believe these days how many companies in the UK were manufacturing small personal computers in the late 70s, early 80s. I think at one point somebody counted several hundred different, and of course you can see some of them around the room here. But actually, one reason for this was it was relatively cheap to start a company to build a personal computer, because all you needed was the semiconductor chip manufacturer's books of parts, and you could design a circuit board. You could even hand wire them. A lot of my prototypes were Vero wired. If people remember Vero wire, it was a wiring pen. You could get a standard Eurocard. You put little plastic combs in it, put sockets in for the chips, and then wrapped this polyurethane insulated wire around the pins, ran them around the cones, the combs, that's what the word I was looking for, and then to the far end, wrap them around again. Then when you soldered the joints, that melted the insulation and made a connection, but the insulation meant you could run lots of wires through the same combs without them shorting. And all of my home-built stuff was prototyped in that way. So you could prototype even something of the scale of the Atom, and it would work on that technology because nothing was going much faster than about a megahertz. Today, this would be hopeless because now we're at gigahertz and none of this stuff would work. But at a megahertz, it worked fairly nicely. You see, this says also available ready-built, a bit more expensive. I think this was the last thing Acorn sold as a kit. We'd established with the Atom that the market for machines like this was significantly potentially larger than the number of people who knew which end to pick up a soldering iron. Everybody's picked up a soldering iron by the wrong end at least once, haven't they? But you only do it once if you have any learning capacity left. So, the Atom was doing all right, and Acorn was thinking about what it should build next. Now, here's a picture from the early days. Of course, the story is well known. We got to hear that the BBC was looking for a computer to support a series of TV programs, and we had this concept of the Proton, and we started developing it. I like to show this picture just to, that's me sort of closest to camera, and I like to show the picture because it proves that I did once have hair, right? And we still haven't worked out who this is. Okay, that's Alan Wright, that's me, and we're not sure who's in the rear view here. And people have been working quite hard to try and find out who that is, but without success yet. Anyway, as a result of the famous week of development, where we turned the Proton from a concept into a working prototype in 4 days, Acorn secured the BBC contract, and so we produced the machine. Again, you've got these around here. And that was first shipped in 1982, from about the beginning of 1982. My first daughter was born in January 1982, so these things kind of lock into my family history. That was the marketing department's view of the BBC Micro. My view of the BBC Micro was a bit more like that. It's a big printed circuit board. It's what you see inside this box. If it's fully populated, it has 102 chips on that board. And the chips are all fairly anonymous looking black rectangular things in those days. And you know, I guess most people are familiar with this, but the stuff over here is memory and those are the ROMs. The key chip, of course, is the microprocessor, which again is a 6502. In the case of the BBC Micro, it's now running at 2 megahertz rather than the 1 megahertz that was typical of the Atom and Apple II and so on. But otherwise, all the other, that and all the other chips on this board are standard off-the-shelf parts with 2 exceptions, okay? And the 2 exceptions, I mean, they don't look very different, and they're not coming up. The 2 exceptions are those 2. And those are the chips which, if you've played with the innards of BBC Micro, you will know as the video processor and the serial processor. And they were built using Ferranti ULA technology. ULA is uncommitted logic array. So it's a semi-custom chip. There was a single layer of metallization. Ferranti produced a standard layer of transistors and silicon underpasses, and then you had a single layer of customization where you could wire these transistors together to form logic gate circuits. And each of those ULAs replaced about 10 or 20 standard chips. So the board would have had about 30 more chips on without those 2 ULAs, and it wouldn't have fitted inside the case. And that was my introduction to chip design. Okay, those are the first occasions when, instead of just buying an off-the-shelf chip and working out how to use it, I'd had to get involved in designing the chip itself, in this case at the semi-custom level. But interestingly, that basically set the direction for the rest of my career. I mean, I've already talked to quite a few people in the room who say the BBC Micro set the direction for the rest of their career, but that's true of me as well. And I've been in the chip design business ever since. And you know, we had fun with the video ULA. The serial ULA was just worked. The video ULA, I think because we were pushing very hard. Typically, Ferranti was used to users that used about half of the devices on the chip. And on the BBC Micro video processor, we used 95% of the components. And so it got a bit hot. And when it got a bit hot, the display started twinkling. And when the display started twinkling, people didn't like it. So there's a big fat resistor there. And that's there to drop the voltage onto the chip to move some of the excess power off the chip into the resistor, and caused me to make several trips to Gem Mill in Oldham to try and sort things out. But in the end, we got things fairly stable. Now the BBC Micro went on quite well. It became a sort of central component both of the BBC's TV programmes, which was its original concept, but also of the government's Computers in Schools programme. So something like, I think slightly more than half of the computers that went into schools under the Computers in Schools programmes were BBC Micros. So lots of people cut their programming teeth on these machines, and more by good luck than good judgment, the machines turned out to be very robust. So they would withstand decades of primary school kids hammering away playing games on them or whatever. Knowing what I know about the margins in the design is really quite surprising. One of the features, if you've looked at the BBC micro circuit diagram, is that somewhere in there, there's a little resistor pack of 8 resistors wired across the 8 data bus wires, pulling them high, okay? People have seen this. Do you know the origins of that resistor pack? It was my finger. I discovered on one of the early PCBs that if I held my finger in a particular place, the machine started working, and if I took it off, it stopped. And now I didn't have enough fingers for the expected 20,000 production. And in fact, if you look at the numbers, probably the 6502 data bus in the BBC Micro is overloaded by about a factor 3. So that pull-up pack is just helping it a bit. It's better at pulling down than up, so we help it a bit more with the pulling up. And everything works. The other story, well, there are many stories. I hope I get this right. Those parts along the bottom there, they're National Semiconductor 81LS95 tri-state buffers, okay, and they're used for multiplexing the addresses onto the DRAM array, which is sort of there somewhere. And a lot of, well, several other suppliers came with plug-in replacements for the 81LS95, which had identical specs. And we put them in the machine and it didn't work. And we never knew why. So we stuck with the 81LS95 and it kept working. And again, we never knew why. One of the features of the machine was that it was a bit temperature sensitive. So if you talk to our Australian distributors, Australia is a bit warmer in the summer than the UK. And they had quite a lot of trouble with the machines getting too hot. And in fact, at Acorn, we eventually got a thermal test chamber to put them in. And if you put them much above 30, you'd run into difficulties. They were okay up to about 30. So it was, there weren't big margins, engineering margins. So the fact the machines kept working is quite remarkable, as I said earlier. But they did, so that's a good thing. But we learned a lot from this. So later, when it came to thermal testing the ARM systems, we put those in the same thermal test chamber, and we had to take the floppy disk drive outside because we ran them up to 120 degrees environmental, and they were fine, except the floppy disk, which would get a bit too floppy at that temperature. So we got the computers in school stuff. That was a photo I had of the early days. The man in the front admiring the BBC Micro case cover. Do you recognise him? Sorry?
Baker, is it?
Yes, it's Baker. It says a government minister here, which is a bit of a clue. And again, that's me in the background on the left, again, still with hair. Chris Turner at the front. Herman Hauser just behind Chris. Chris Curry lurking on the right. And there looks to be somebody behind Kenneth Baker, but I can't see who it is. So that was me in a suit, which was quite rare then and almost unheard of now. Now, the BBC Micro, of course, went very nicely. The BBC's original estimate of, well, I thought they said 12,000, but I've seen people quote 20,000 recently as the expected sales number. Of course, that turned out to be a hopeless underestimate. And we ended up shipping about 1.5 million of the machines. And that put an enormous strain on Acorn, which was a small startup company, coping with over 1 million machines out there with customers with varying degrees of happiness with their machine. Acorn didn't really have to learn anything about selling computers. the things walked off the shelves faster than they could be made. That was true of a lot of computers. I mean, it wasn't just the BBC Micro. I mean, Sinclair, who was a competitor for the BBC contract, sold far more machines. I mean, sold about 5 million Spectrums in the time. Acorn sold 1.5 million BBC Micros. So it wasn't just Acorn, but everybody completely failed to anticipate the public demand for getting their hands on computers when that became possible. So the things walked off the shelves, and Acorn really never learned how to sell anything. It just went. There's lots of stories to go with this, but of course I was in the R&D area, so our job was to work out what we should do to build on the success of the BBC Micro. Obviously we had contractual obligations to build all sorts of fancy bits to go with the BBC Micro, such as the Press-Tel adapter and the teletext adapter, so that the BBC could distribute software by telesoftware. You know, that's sending bits in the blank lines of the television display that the box would capture and load onto the machine. Remember, this is before, well, I almost said before the days of the internet, but of course that's not true. The internet's been around since the early 1960s, but it was before the days of the World Wide Web and general public awareness of the internet as a way of distributing digital information. So it was done over the TV channels. And while we were, but we still had to think about what went on beyond the 8-bit micro. 16-bit micros were coming from all directions. And we built second processors, you know, the BBC Micro. All BBC Micros can interface to a second processor. And we built second processors with pretty much every chip that was available at the time to evaluate them. And the upshot of that was we didn't like any of them. And we had two good reasons for not liking them. Most of the 16-bit processors that came out in the early 70s were based on conceptual designs from mini computers in the 1970s. So the mini computers had gone to 16 and 32 bits, and the microprocessors kind of followed. And that meant they got increasingly complicated and detailed instruction sets. And the impact of that on the processor was that they had very poor real-time response. Real-time response means, you know, when your disk drive delivers another byte to your disk controller, the disk controller likes to interrupt the processor, and that's a real-time event. And the processor has to go and do something before the next byte arrives, or you lose data. And on a single density floppy disk, a byte of data arrives every 64 microseconds. But we were going to double density, naturally, like everything. So now you had a byte every 32 microseconds. Well, a 6502 can cope with that easily. But, for example, the National Semiconductor 32016 had a memory-memory divide instruction which took 360 clock cycles at 6 megahertz. So it took 60 microseconds to execute one instruction, during which it was not interruptible. So there's no way that processor could reliably handle double density floppy disk data transfers without hardware support. Of course, NatSemi would sell you a DMA engine at additional cost that would do it, but we thought, you know, the processor should be able to do that. So the other thing that we found from our studies was that however nice or fancy the instruction set was, it made almost no difference to the performance of the processor. The thing that determined the processor performance was the processor's ability to use memory bandwidth. So if your memory was, if you could use twice the memory bandwidth, you get twice the performance, pretty much irrespective of how nice the instruction set was. And these 16-bit processors were not at all good at exploiting the available memory bandwidth from standard commodity memory. And the memory was the most expensive bit of the computer. So if you paid your money for this memory and it had a certain bandwidth, but your processor could only use half of it, we saw that as very wasteful. So we were basically sitting there scratching our heads when Andy Hopper or Herman or somebody started dropping papers like this on our desks. And this paper is a seminal paper, The Case for the Reduced Instruction Set Computer. And this one's written by Dave Patterson and Dave Ditzel, then at Berkeley. And basically what it says is that designing a microprocessor, which is a single chip computer, central processor, is not the same as designing a mini computer, which is mapping a processor onto many chips. You have a lot more options when you're using multiple chips. When you're designing onto a single chip, you have a finite resource in terms of number of transistors. And if you want the best performance from those transistors, what you don't want to do is burn a lot of transistors supporting complex instructions. What you want to do is support the basic instruction set efficiently and then use any transistors you've got left for more important things, where the most important thing is what's called pipelining. Okay? And pipelining is a technique where instead of a processor such as the 6502, which fetches an instruction from memory, decodes it, and then executes it, in a pipeline processor, you fetch the instruction, then while you're decoding it, you fetch the next one, and then while you're executing the first, you're decoding the second and fetching the third. Okay? So basically, you're, with that simple example, tripling the throughput of the processor by using all of its resources at the same time, but on different instructions. So this paper argues, pipelining is a better use of your transistors than giving your processor a very complicated subroutine entry instruction, for instance. And in particular, at UC Berkeley, there were similar stories coming from Stanford, and an older story about the IBM 801, which was quite similar, and even Cray supercomputers kind of are designed along these principles. But it was the Berkeley work that we found most convincing. And they'd had a postgraduate class of students design a processor in an academic year that seemed to be better than any of the commercial semiconductor manufacturers' processors. And so we began to think, well, maybe if you can get it through a postgraduate class in a year, maybe we can do this. We were getting fairly cocky at Acorn because lots of things we did seemed to sort of turn to gold. So we kind of felt we had a bit of the Midas touch when it came to technology. So we had this sort of high degree of confidence, though nobody in the company had ever designed a processor before. Okay, so we took lessons from the Berkeley work and started sketching designs for what would become the Acorn RISC machine or ARM processor. RISC was its middle name, so it's clearly based on this American research. And that really got underway in about late 1983, and we got the first silicon in April 1985, about 18 months later. And so that's 40 years ago, and we had a big do back in April in Cambridge at ARM and at the Centre for Computer History to celebrate the 40th anniversary of the first ARM silicon. So how did we design it? Sophie Wilson sketched an instruction set. We took a number of ideas from the Berkeley RISC-1, but we also changed some. Those of you who've studied the Berkeley RISC-1 will know it implemented register windows, which meant you had a very large register file, and when you entered a subroutine, you basically stepped a window across these registers so that you didn't have to save or load any of the registers. You got a new set. And that made subroutine calling efficient, but it also made the register bank expensive. So we didn't use that. That did end up getting used on the Sun SPARC processor. So the SPARC inherited the register Windows concept, but we were aiming for lower cost. So we didn't do that. We did something a bit similar for the interrupt handling, but anyway, Sophie, who'd written all of Acorn's basic interpreters, knew what was needed to support a high-level language, right? So she sketched out an instruction set. I turned that into a microarchitecture, bit of which is there. And I wrote this, I've been asked about this already by somebody today. How did you describe the ARM? Well, I wrote what's now called a register transfer level model of the ARM, but I wrote it in BBC Basic because we wrote everything in BBC Basic. And it took 808 lines of code. And that kind of expresses its simplicity. If you look at a modern ARM model, it's probably 100,000 lines of Verilog. Okay, but this one was early and simple. And I thought this model was lost, but then about 10, 15 years ago, I did some garage archaeology and found a box of floppy disks at the back of my garage, one of which contained the original ARM reference model. So it's been recovered. I said, I found this. I went to ARM and said, I found this. Can I sort of put it online, publish it? And they said, no, it's confidential. They later relented, and in fact it is now, I think, in the public domain. Sophie designed the instruction set. I made one or two minor changes to it to sort of make the architecture a bit cleaner. But basically it's Sophie's instruction set. And I wrote the microarchitecture. And then I turned that into what we call block specs. So I took the bits of BASIC I'd written and wrote them down as specifications for bits of hardware. Acorn had recruited a small team of VLSI designers who turned those block specs into hardware and put the chip together. And we had a small group of software people who wrote a validation suite, where the validation suite basically, a program would look at something like the set of shift operations that the architecture specified, and it would then, as exhaustively as possible, test that all those things did what they said they'd do. And in the case of the shifter tester written by Hugo Tyson, if it didn't pass, you got some very rude words at the end. And that validation suite actually lasted for years. It was used by ARM for a long time, evolving as the processor was tweaked, but the basic idea. So I think the entire team was about 10 people who contributed to getting the first ARM chip out. And, well, I've already said this. The silicon arrived back on the 26th of April, 1985. We plugged it into a test card and booted BASIC, and it all kind of worked. There was one very minor bug in the ARM1 silicon, which was, this is the barrel shifter here, and there was some piece of metal that found its way into the wrong place in the barrel shifter, but it only affected a very obscure corner of the instruction set. So basically the ARM1 was highly usable, and we never fixed that. I mean, we fixed it on the ARM2, but we built that for other reasons. How did we design it? Well, that picture at the back there is my original pencil sketch of the chip layout, showing the various functional blocks. On the right is a picture of the chip itself, which is pretty much the same. They're not identical to my sketch. But the main way it was designed, which really comes before the reference model, is expressed in this picture, which is the data path picture. And this shows the major functional blocks. So the register file's there, and the barrel shifter's there, ALU is there. And I sketched something like this out by hand, quite tidily, and then ran it through a photocopier to get about 50 copies, and then started colouring it in for each phase of each instruction to show what was flowing where. And then if I got to the point where an instruction didn't sit nicely and I could see how to make it sit nicely, I would change the master diagram, throw all the coloured in bits away and start again, okay? But I think it only took 2 or 3 iterations to get to the final form. And that basically captures everything that's happening in the microarchitecture model visually. And it was all put together, it all worked. And through this process, I mean, we kind of came into this thinking that designing a processor was a bit of a black art. You know, we visited Nat Semi's 32016 design team in Tel Aviv in Israel, and they were on Rev J of the 32016, and they still hadn't got all the bugs out. And that was, you know, a team of 100 people. And so we expected to find out why this wasn't a good idea. The other thing we expected was that the RISC argument was so clearly valid and strong that it was obvious that the big semiconductor manufacturers would jump onto the RISC bandwagon and get something out there before we could, because they had far more resource. But interestingly, the big semiconductor people were much more strongly wedded to complex instruction sets than we realized. And although the arguments were strong and clear, they obviously didn't see them. Because it wasn't until the end of the 80s when most of the big manufacturers started to see that RISC was a good idea. And of course, you know, even today, you have x86 architectures out there which still use very horrible old complex instruction sets. They make them run quite well because they turn them into RISC inside the front of the machine and then execute them like a RISC thereafter. But I remember going to a presentation by a group of academics who designed an x86 instruction and run length decoder. Okay? Now this is a piece of logic which looks at the stream of bytes coming from memory and works out where one instruction ends and the next one starts. Okay, because x86 has variable byte length instructions. On an ARM, which is fixed 32-bit, it's easy, right? The next instruction starts 4 bytes after the previous one. But on x86, it's variable. And this logic, whose only role was to work out where the next instruction started, was significantly more complicated than an entire ARM processor. So, well, anyway, as you know, the ARM went on to enjoy reasonable success. Many people have asked, how is this possible? And, well, that's a good question, really. Various answers have been forthcoming. I think the RISC concept was fundamental. Had we not had this strong academic argument for simplifying an instruction set, we wouldn't even have started. And we certainly wouldn't have finished had we started. But Herman, in his best thinking, has said that he gave us 2 clear advantages over the major semiconductor competition in processor design. His first advantage was he gave us no people. And his second advantage he gave us was no money. And like all of these things, you know, it's a bit post hoc rationalization, but there's some truth in it. The fact that we were a very small team really forced us to think simply. If we make this complicated, it's never going to work. So how simple can we make it? And the RISC concept very much aligned with that motivation to keep things simple. And the second one, doing everything in-house, it has advantages and disadvantages. And it's not quite true because we did buy in the VLSI design tools that the chip folk used from VLSI technology. But, you know, I've already said, you know, the microarchitecture model was written in BBC Basic, and that was very straightforward. And partly It was possible because of the simplicity of the design. The design was very much based on the Mead-Conway design philosophy. Those of you who've been involved in chip design for a long time will know that at the beginning of the 80s, Carver Mead and Lynn Conway wrote a book which became the kind of chip designer's Bible. And it talked about specific ways of designing chips using two-phase non-overlapping clocks and stuff like that you probably don't want to know about. But we really did keep things simple. And the first silicon was pretty much fully functional to the extent that it mattered. And I left Acorn in the end of the 90s because towards the end of the 90s it was becoming harder to see how we could find the funding to continue the process of development at Acorn. Acorn's education market was fairly flat. The PC was becoming established and increasingly wanted by schools instead of Acorn's more advanced products like the Archimedes. And it must have been, within a week or two of my departure that Apple came knocking at Acorn's door and saying they were quite interested in using the ARM in their Newton product. And but they were not quite comfortable, they saw Acorn as a kind of competitor, not quite comfortable with the ARM being owned by a competitor. So how about setting up a joint venture to develop the processor further? They were knocking on an open door because Acorn had spent the last couple of years trying to work out if they could offload this processor development cost somehow. So I left at the end of July. There was no sign of Apple then. The business was established and running in November. So it clearly all worked together. And of course the focus was the Newton. Apple's first attempt at doing something which they then did a lot better 10 years later with the iPhone. And it wasn't a success in Apple's eyes. But it was an early attempt to do a PDA. It had a pencil, you can see there, that kind of neatly fitted in it somewhere. It was supposed to have handwriting recognition, although that didn't work terribly well. The thing it didn't have that really makes all the difference to these devices is communication. So it was a standalone personal digital assistant rather than a communicating one, which is what the iPhone became. Now it's hard, if you're not familiar with the Newton, it's hard to think how a product as obscure as that's become it really made ARM. But in those days, just as today, Apple was a huge brand in the world of computing. And everybody knew that ARM Limited had got the Apple contract to design a processor for the Newton. So everybody wanted into the ARM. And ARM signed licensees up. ARM's business model was never to make processors. It was always to design them and then license them. And so their success was basically measured by the number of licensees they could sign up. And I'd spent my last couple of years at Acorn trying to work out how a business model for doing this profitably, and my models never worked because if you lived off royalties, royalties are small and late, and your cash flow is awful. And to cover the cost of the company, you'd have to sell millions of processors, and we couldn't imagine selling millions. Yeah, I know that sounds silly, but that was the case. Robin Saxby was brought in to lead ARM, which basically was built around the 12 people who worked for me at Acorn. I'd left, but those 12 people moved across, and Saxby was brought in as CEO. And he added one component to the licensing model, which is the upfront license payment. So if you want to build ARM into your products, you do have to pay royalties, little and downstream and late, but you also have to pay an upfront join the club fee. And I think, at least with their first few customers, every new customer paid twice the joining fee of the previous one. We'll talk about exponentials a bit more later. But the upfront license is wonderful for cash flow because it's big and it's early. Royalties are small and late. Until you've been there a very long time. I mean, ARM's royalties are now, I don't know, a third of their turnover is royalty payments, but it takes a very long time to build that up. So, ARM set off, and they turned out to be in a good place. Again, this is more by luck than good judgment. But it turned out that it was the beginning of the 90s when ARM was formed that people started to talk about systems on chip. Up to the end of the 80s, if you built a processor, the processor was a chip, a microprocessor. But now you've got enough transistors, thanks to Moore's law, about which more later. You got enough transistors you could start putting other stuff on. And the idea of a system on chip is that the chip has not just the processor, but it has most of the other system functions there, possibly not including the memories. So the memories still tended to be separate chips. But if you want to design an SoC, then firstly you want your processor to occupy as little of the space as possible, so there's as much room for everything else as possible. And ARM's simplicity and small size meant it was well suited to that. And secondly, you have a power budget and you want the process to use up as little of that as possible. And again, the ARM happened to score very well on the low power side. So its low power and small size made it an excellent fit for early SoCs. I mean, the transistor resource available today is monstrous. Okay, but in the early 90s, this was just beginning to become possible to put system functionality on there. The example here, that's probably not going to work. Now that's the ARM core in the top left of the chip. And the rest of that, well, the stuff around it is processor related, memory management, cache. But then you've got floating point stuff and DMA and video and all sorts of things. So you can put a lot of functions on the chip. I'll show you a modern chip later. You can't really tell what anything is anymore, but there's so much of it. And, the success has sort of developed exponentially since the company was formed. So the last number I heard was that the total number of ARM-powered chips shipped to date is past 300 billion. I said earlier, selling millions was unimaginable. They're now running at 30 billion a year, I think, in terms of the manufacturing. And, the population of the planet's about 8 billion at the moment, something like that. So, if you're not buying 3 or 4 ARM processors every year, you're not doing your job properly. I mean, there are about 12 ARM processors in that, for instance, so the numbers stack up fairly quickly. So that's the ARM story. I'm now going to move on to...
And our fascinating talk with Professor Steve Furber continues in part 2, which will be on the channel shortly. Please subscribe if you haven't already done so to catch that episode soon. Thanks for watching.